The Portuguese NRAN.
You still work for them? Don't want to tell a mess. Welcome, everybody. I'm glad to have so many people here this morning. So it's early and we had a dinner last night. This session is about IP version 6 and has the martial title IP version 6, Dead or Alive. Somebody pointed out that it should rather say Alive or Dead. Anyway, we start with Carlos Friasas. He's from FCCN in Portugal. And he is very much involved in many international activities in IP version 6. And he's talking about, just a second. Oops. Is IP version 6 deployment on track? This is the right one, I think. Please go ahead.
Good morning. Firstly, thank you, you all, for being here so early in the morning. Well, perhaps the best way of starting is to ask for a show of hands to know which people are already running IPv6 on their own network. So let's see. Well, just about half. That's good, but in good truth, you are not probably the best of the samples. So you don't represent what is really happening at a global scale. You are mostly from the network, the academic networks. So this is just one of the parts of the internet. There is also a big question when you start to deploy IPv6. Are you doing it completely? Can you say IPv6 is running on 100% of your network? Well, in that case, even I can't raise my hand on that. So This is probably one of the bigger problems. So I have some slides to show. I'll start about focusing on some myths. Then I'll make a brief some brief words about how the global addressing system works. Then to the hot topic of IPv4 exhaustion, that is for most of the people nowadays the bigger rationale for having IPv6. Some people are still trying to run away from it. So in some way we can understand that because working on this topic we still see frequently a lot of operational problems. So we also in the scope of the paper we also did some basic tests to see how the IPv6 network was working, if the behavior was similar to IPv4 or not, but it's just really a basic mechanism. So this talk is about the network perspective, not about the applications. We all know that we need the network to run applications, but if we don't have the network ready, the IPv6 applications will not be able to run. It's just perhaps the best time to do some publicity. So we have been working on 6DIS, which is the IPv6 dissemination and exploitation project, which is an IST project, and has been working also, apart from deploying workshops around the world. In developing countries, we also developed a valuable IPv6 e-learning tool. So, going to start looking on numbers, looking at both the IPv4 and the IPv6 routing tables. We see about 700 autonomous systems and almost 25,000 autonomous systems. So most of you may ask, so these numbers are very different in both worlds, but what does this mean? For me, this number is very important because if the IPv4 world, if the IPv4 internet needs and has about 25,000 independent networks with its own proper routing policy, having only a very, very small part of that on the IPv6 world means that IPv6 has still a long road to go. So, starting about myths, well, like me, probably most of you also have continuously heard that IPv6 in Asia is much more advanced. Well, from data, we can, for instance, from the address allocation data, we can see that the numbers show that the European region is a bit ahead. We can say, on the other hand, for products that Asia is really ahead. So the Asian industry is starting to have much more a much more broader portfolio of IPv6 enabled products than the European industry. But in terms of network, well, and this is not related to traffic, it's just related to one of the simplest things when starting to deploy IPv6, which is getting the address blocks. In this matter, we can see from the numbers that Europe is leading. So another myth is that IPv6 doesn't exist. It's just, this is almost a common myth, mostly outside the academic area. So IPv6 is just some things some guys are theoretically speaking. No, today and some years back, we can start say this is not really the case. So the academic area is far ahead and have deployed almost in parity IPv6 like they deployed IPv4. So for the academic sector, the chicken and egg problem is solved, and we have a big degree of certainty that IPv6 applications will run with a fairly amount of performance within academic networks. So there is another myth that to see IPv6 take off, we need end users to ask for it. Well, this is not really the case. We should really need to convince the network administrators, not only the local area network administrators, but also the transit provider network administrators. So, the end users really don't care about which protocol is running on the network. They just want to see their applications work. So, and there is also another issue that is that getting applications to be IPv6 enabled is really a serious problem. Well, it's not if proper applications program interfaces are really architectured. So you should use the proper APIs to have the applications to use both IPv6 like IPv4, just depending on if it's available on the network. So the other big miss, and this is probably because most people doesn't understand how address blocks are distributed from a global perspective. So we often say that, we often listen that Asian countries get an hard time when trying to get IPv4 addresses. Well, from the current global distribution system, that can't happen, because when Asia has problems getting address blocks, America should get the same problems, and Europe should get the same problems. So there is a proper way of distributing IPv4 and also IPv6 address blocks in place. So this is just a miss. So for one of the most current hot topics is guessing when IPv4 will be exhausted. So we have about 40-something still available /8s to be distributed worldwide. I think last year, for the 5 regional internet registries, IANA distributed about 12 or 13. So if we do a linear approach from the 40, we can envision that we'll still have IPv4 addresses to distribute worldwide by more 4 or 5 years. But when we look at this issue, we should get the data from the proper places, which is IANA and the regional internet registry. So this is now I'll show you 3 slides from probably the most comprehensive work, that is the work of Jeff Houston from APNIC, which is the Asia Pacific network, the Asia Pacific Regional Internet Registry. So this was the prediction in 18th of April. So this is about 1 month old. His mathematical study pointed out that IANA would run out of addresses to distribute to regional internet registries by mid 2011, and then the second date is the buffer that the regional internet registries have to assign their members, their local internet registries or national internet registries, which in this case with Jeff's predictions was about 1 year. And then on mid-May, he changed something in his algorithm, so he started using a different mathematical model to predict the growth, and that resulted in those 2 dates changing to just the last day of 2009, and then you can also see that that 1 year buffer between the IANA pool getting exhausted and the addresses that the RARs can still keep handing out to their members also decreased from 1 year to 8 months. But well, if you consider scary this date that is about 2.5 years away from us now, well, there was some events that once again made Jeff's predictions go a bit ahead on time. So these 2 events, which was the returning of 1/8 to the IANA's available pool, and renaming that /8, which is 196, from various registries to AFRINIC, which is the African registry, made that the first date advanced almost 4 months, and the other one also 4 months. So in this case, the first event, adding 1 more /8 increases the time that the IANA available pool will be exhausted, and the second one means that AFRINIC, by getting those that new /8, will take more time to get the next /8 from IANA, from the global registry. Well, some people don't really believe this will happen, so they will have to look for alternatives. So probably the most common alternative is doing several layers of NAT. So perhaps in 5 or 6 years' time, we'll start to we'll start to become not network engineers but net engineers to manage with the several layers of NAT. The other thing we have been listening when talking to people about this issue is that the exhaustion can cause a phenomenon that is the appearance of a black market of IPv4 addresses. So the whole world is currently using IPv4 addresses. So for those which can't or don't seem to start relying on IPv6 because they say it's not cost effective and so on and so on. What can really happen is the companies that have big blocks of IPv4 addresses and are not using it maybe we'll start to sell them to make some money, despite addressing by definition it's not property, but well, sometimes the theory is different from practice. A third approach will be do nothing, sit and wait, and hide head in the sand. Now, operation problems. Those two graphics on top are from CAIDA. Well, CAIDA, we already had a presentation from CAIDA in this conference, but these two figures are mostly important to show how the core of the internet in terms of IPv4 is so attached and aggregated, and how the IPv6 internet has a bigger amount, a very lower degree of aggregation. So it means the core networks are a lot less, just like I said in one of the first slides, and I'm remembering it again on this slide. So there is, well, ideally when we have IPv6 in a mature state, we would have a similar graphic from the IPv4 and the IPv6 internet. But when managing IPv6 network, and I see some faces on this room that are managing IPv6 network with other that manage connections with other networks, we still see that tunnels are a big problem in the IPv6 internet. For instance, you can have the path for IPv6 commercial internet in America going through the Far East to Asia and then to America. When the IPv4 path is direct between Europe and America. This is probably also because there is a significant lack of IPv6 transit providers offering the market. So this is also a very attached problem with how the market is behaving, about market behavior. So we also have a lot of filtering issues. Well, you may say that this is still a thing that happens very often in the IPv4 world. But what is hindering IPv6 is that the response that you get from other networks to fix their filters is a lot more hard to get than if you have the same issues about IPv4. So if they have some problem with IPv4 filters, they will get a lot of complaints from their customers. And well, for most networks, IPv6 is just a play toy, and they will not get that many complaints, and so they are not as keen to fix it. There is also some nagging operational problem, which is while in IPv4 most people register their objects in a database, so can other networks can automatically validate the announcements that are happening in the routing table at the BGP level. Well, this is something that we also need on IPv6, and I don't know how many of you have run into this, but from time to time we know that a new network outside the academic world is deploying IPv6, but if they don't register their network objects in a database, GEA will not accept those prefixes. So the access to those networks will not work. There are two things to note about here. The first one may perhaps be that GEA is working over IPv6 in a production way, so they are treating IPv6 equally like they do for IPv4. So if they don't accept an IPv4 prefix that isn't registered, they will not accept as well the IPv6. And the second note is that, again, most people don't register the objects in the database because they don't think IPv6 is production. Now about the next chapter of the presentation, which is testing how trying to compare the performance of IPv4 and IPv6. We did a very simple approach and work. So we had some Unix scripts running for about 1 month. We chose, and this is probably something that we may improve in next phases of this kind of work. We chose some targets that already have Quad A records registered on the DNS, and we chose a sample of hosts all across Europe. And the method for this simple performance test was sending ICMP probes, so pings, every 15 minutes, and look at results later. So the next slide will show some average values. What you will see in the graphics means that when you have a point below 0, it means that the average of the averages latency is better on the IPv6 than on IPv4, and that's the rationale for the UP. The UP guy is that the IPv6 latency can get better than IPv4. So we targeted some other hosts inside networks connected to GEA. We targeted commercial IPv6 networks also from Europe, and other ones from from the United States, the Vatican, which is, well, it's not formally an European Union country, from Japan and Russia. And we can see that we have a lot of points next to the zero line on the NRAN side, and that really doesn't happen on the other cases. So the main conclusions about this is that the academic world's performance towards hosts from FCCN to those networks are okay. And we have an interesting case that I will talk later, which is from Lisbon to Dublin. That is the value that is the lowest. So the IPv6 performance is the best when compared to all the others. The results towards commercial internet are disappointing. Well, as I said, probably they are not treating IPv6 as production quality. And outside the EU, we've seen the Japanese case it's the best. So there is also the case of Vatican, which is served through GAR, which is inside GN2. So the result was the expected one. So back to the Japanese and to the Irish case. Here, why do we have an IPv6 latency lower in lower than the IPv4 latency? Just because the IPv6 path goes to Lisbon, to London and Dublin, and back from Dublin to London and Lisbon. And we also found out that from the IPv4 network, we have Lisbon, London, and Dublin, and then the traffic gets back to Lisbon via Paris, Geneva, and Madrid. So by doing this, we accidentally found out that IPv6 can, in some way, be a tool to improve how the IPv4 network is deployed. So we have the same path, so we should have the same performance between the IPv4 and the IPv6. So there is also, I'm running short on time, so there is also the Japanese that we had one of those 15 minutes tests. We had the higher difference in favor of IPv4, like 140 milliseconds, and surprisingly, the highest value in terms of having a better IPv6 test was about 56 milliseconds. So, but we also have to have in mind that this target is unicasted, so we could be doing the test back to Japan in the IPv4 network, and we could, at that time when we get the good result for IPv6, to be testing one of the mirror instances. Well, I'll have to skip this benchmarking word, so and perhaps just point out that from RIPE the data we can see that about 12 or 13% of local internet registries that are members of RIPE already have an IPv6 allocation. So the other 80-something percent of networks that are members of RIPE still have to request their IPv6 block to start their IPv6 work. So again, on IPv6 routing, if we look at the AS numbers, Europe is again leading largely. Also on DNS, we have seen over time that top-level domains supported by at least one name server, that number has increased over time, but it's not on any exponential growth. So conclusions, IPv6 is quite like IPv4, so there is not really the reason to be at this, unfortunate state. IPv6 needs better applications to be deployed, and from the market point of view, what we need is to make that IPv6 brings benefits to both sides, not just end users, but also internet service providers. So the main conclusion will be that IPv6 is not really that, but it needs to get on the next step and become production quality. So this is the main conclusion, and the question is, what can be done to change this? Yeah.
We have time for one question, please. If there's no question, then I have one. How about IP version 6 and security? I mean, nobody runs a network without security measures today. And for example, are firewalls fit for IP version 6? Or is IP version 6 traffic simply open? Or is it completely blocked? Or what's the status?
That's probably one of the problems. Security products that support IPv6 do exist, but the portfolio of products is not wide enough, in my opinion. So this is something that will evolve over time, and hopefully, it's not a bigger question. And this is a funny question because over time, IPv6 has been advertised as something that will bring more security, and per se, that's not something.
Thank you. Thanks again. Always. We are very short on time, I'm sorry. Our next speaker is Kari Hutanen. He's from Tampere Institute of Technology. You have a PowerPoint version.
Yeah, that's
Okay.
I think I'm going to get it full screen there. Okay, we have some problem with the Danish encryption here, but okay, let's try. Sök efter. Control M. Okay, thanks. Yeah. Okay, good morning, ladies and gentlemen. I'm here to present about this case we did on this home entertainment or home network project in TUT. And it was the idea that we could utilize IPv6 in home networks with the help of this transitional technology called 6-to-4. We also found out a few other applications and kind of solutions to certain problems that might come into existence later, or at least when this kind of VPN connections to home and corporate home networks, the number of them increases. Right, so the problem what we are trying to solve here is the increased usage of NAT and private IPv4 network space. This creates this kind of router problems and conflicts in that sense that, well, the users, they aren't really a network engineers, so they don't configure different networks so that they could be used most efficiently. And this kind of scenario where we have a lot of private networks starting, for example, this 192.168.00/24 network, we might have several of these in several places, in homes, in corporate network, in Wi-Fi hotspots. And the problem arises then when we try to connect to these networks by utilizing this, for example, this Wi-Fi hotspot. If we try to run here a VPN to home network or corporate network, we have here, we might have here address conflict, we might have here a root conflict, and the system just doesn't work. Obviously, this kind of home users probably won't care. Okay, they just think that, okay, this is a kind of some stupid error and cannot continue working. But on the other hand, it is possible to make this scenario work by utilizing some other technologies there. Also, one other thing is that when we are thinking about the interconnected homes, that we have, for example, a future home where we have this kind of IP network and we would like to share information between these home networks, then we have a kind of trouble bridging these networks or making them work together, at least directly with the routing the traffic, because we have exactly same network or might have exactly same network here. Of course, we can solve this with IPv4, or at least solve it partially. We can do this kind of network design that we actually take these kind of smaller network blocks, because smaller network blocks obviously overwrite the bigger one in the routing tables. So this kind of scenario might work, that we try to pick up that kind of network that is more likely to be unused of the private network space. So maybe, for example, randomizing some numbers here, maybe making the block smaller, and trying to coordinate all this. But when we think about these different networks and then think about configuration and coordination, it's obvious that you cannot actually expect that the home network users will try to select the network they are using, IPv network they are using. Even some of the corporate IT admins, they just start, for example, from this 172 block in the beginning, and then try to use that one. We actually have here in TNC, we have this 172 block in use in the wireless network here. And luckily I noticed that none of this kind of IPv4 private networks I use with my VPN isn't on that block. But if we look at this picture and how feasible it is to try to coordinate this, we can find out that it's not really feasible to try to solve the problem this way. Okay, the proposed solution. This kind of interconnected home networks and even corporate networks, that even this problem might be somewhere in the future, or maybe it's not a current problem. There at least haven't been a lot of talk about it. So we might as well use IPv6 to solve the problem. This would mean that either we should distribute, the operator should offer IPv6 service and route networks to this kind of home users or corporate entities or Wi-Fi hotspot operators, but I don't think that's going to be the case because well, they just don't see the need to do so. And that's why we were thinking about that how could we do this also without the operator support. And 624 was in that sense one option to do it. Of course, it requires operator support that you have to find the 624 relay router somewhere in the internet. But then again, some operators already offer this and might offer it more in the future. And what we did is the inspiration came from Terena conference in Poznan, and there was this presentation about using OpenVRT and these Linksys boxes to integrate their 624 and IPv6 on that kind of open source platform. And so we picked up a few of these boxes, and nowadays it's much more easier even to get the 624 running there. And with the one public IP address, we managed to get this kind of /48 address block to the home network to be distributed. And it's routable, it's unique IPv6 address space, and it utilizes this 624. What we did this in this home network project then was that we also integrated OpenVPN in this OpenVRT box. And with the help of that, we could get the IPv6 connectivity everywhere to home network and even through it. So actually, when I use my laptop here and connect to my, for example, home network router there, I get an IPv6 address. I get the, and it's a native IPv6 address in IPv6 internet, and I'm able to connect to all the IPv6 services through it, even if there is a NAT translation or a private network, IPv4 network here. And now, even if this local IP and VPN IPv4 address would be in conflict, I still would have this IPv6 address from my home network and maybe be able to access those home network services there. Okay, here is more how it actually works. I'm not sure how well this is shown to the rest of the crowd here, but then you can of course always check my slides about this one. So the idea basically is here that we have a home router. It makes a DHCP request, gets a public IPv4 address, registers it to dynamic DNS. And this is IPv4 address we are registering there. It creates 624 network address based on this IPv4 address, reconfigures interfaces and router advertisement demo on the home router. And after that, it's just IPv6 auto configuration for home services to acquire the IPv6 address. Of course, if we want to use a name service, which is much more nicer than the IPv6 addresses, the home services should register their own acquired IPv6 address to maybe home DDNS in home router or maybe one in internet. It's depending, of course, if the service wants to be available through IPv6 public internet or only locally in the home network. Right, and when this user terminal wants to access these services, it makes this DNS query, receives a response about the home router there, and then creates this OpenVPN tunnel to the home network. We used OpenVPN because with that it was the easiest and most flexible way to get the IPv6 to the terminal. IPv6 over IPv4 IPsec, for example, it doesn't work so well. The implementations doesn't actually support that so well. So this OpenVPN was our selection because of that. And now this OpenVPN tunnel, it makes this kind of connection directly to the home network, and it bridges the home network over the tunnel. So we can actually use their IPv6 auto configuration also for the terminal to receive its IPv6 address. And then there is just this that user terminal queries for home service address either from the home router DNS or from the DDNS server in the internet, gets your IPv6 address in response, and now now the terminal and the user is able to access those services at home. Nothing kind of special here. It's just utilizing the internet technologies and all those components we already have available. So the advantages of this solution. With the cost of only one IPv4 address, which is used by the home network router there, we can get a routable and unique /48 IPv6 network with the help of 624, but even without a local network support, in that sense that we can reach this 624 relay router. It's an anycast address, so it tries to when we create the 624 tunnel there, it tries to find out the closest one. This means that we have enough unique routable addresses for home service servers, mobile terminals, and without no IP or root conflicts. Maybe what's even more important or interesting is now that we have this solution, we have a full IPv connectivity, and it's not just between the terminal and home network, but also between networks and the whole IPv6 internet. The terminal is able to obtain the secure IPv6 internet and home service connectivity anywhere without the local support, because we use this VPN. We don't actually care about what the addresses, the IPv4 addresses in between are. We just make a VPN connection, get the IPv6 over it, and that's it. This way we can get the full connectivity from terminal to IPv6 internet and back everywhere. We can actually utilize this solution to that we have multiple terminals at one or few this kind of VPN termination points, and this way these different terminals have this two-way connectivity between each other, even if there would be this kind of firewalls in between, like in, for example, operator networks. Of course, this enhanced IPv6 connectivity then makes it possible for home networks and terminals to run all kinds of applications and services without the need to bother with issues like application level gateway support in that home router, STUN, or other this kind of NAT traversal issues. Well, this solution isn't without disadvantages also. The 624 IPv support, well, it exists in routers, has existed there for a while, but then these commercial home gateways and slightly lower-end network appliances, they lack the support for these, and especially running IPv6 over IPv4 VPN. It would be easy to implement this same solution in this kind of Linux or BSD-based products, but okay, here comes the problem. But vendors need the customer demand, and the customers do not know what to demand. There was this first presenter who was talking about also about this issue. Well, the customers and users, they don't really care that do they have IPv4 or do they have IPv6. They want something that works. And so this concept and use case must be proven useful perhaps to the network equipment vendors, and for them that they can offer different kind of services or better services with the help of this system. Right, IPv6 support in terminals is almost there, but there still exists this kind of usability problems and technical issues like that, what I already mentioned, running that IPv6 over IPv4 VPN. There are also sometimes this kind of DNS resolving issues when the terminals try to make this DNS request. For example, there might be some terminals that will try only this IPv4 address record there and don't work properly, that they would ask this IPv6 DNS record there. Also, this DNS issues, because this solution relies heavily on this kind of dynamic DNS, this can be seen as disadvantages for the concept, as we need this kind of additional IPv6 capable dynamic DNS service, either in the home router or in the internet. There is a partial solution for this. It is possible probably to utilize also other service discovery methods with this bridged VPN, but actually doing this or solving this problem and researching it is already identified as a future work issue. Challenges and future work. Well, the adoption of this solution technologies, will depend heavily on how useful vendors or service providers see to need it to include in their products. Regular vendors need this kind of market demand, and market needs to know what to demand. But like the first presenter said, it isn't that the market will demand that now I need IPv6 to my home network. It's more like that, okay, they see cool services, and this is kind of just a transport layer or this kind of enabler of this kind of new services. One possible approach would be that if this kind of community network builders that are using this kind of embedded open source Linux boxes, they would see that, okay, hey, we can provide IPv6 connectivity and we can provide some much nicer services like SIP services without the trouble with not over this kind of solution. They might be interested and then maybe this kind of likely route would be this kind of community network builders like maybe Phone, VPS is a Finnish one, and those interested to add this kind of functionality to their already customized routers. Of course, to get these kind of companies to add the functionality in their products means that this concept must be tested, it must be polished, it must be packaged that, okay, this works now, try it, and this is not just an academic hobby or something like that. There still exist some issues which need to be worked out, like DNS and other service discovery. Obviously, we need to set up some IPv6 firewalling security there. And in terminals, maybe one of these key challenges is this IPv6 over IPv4 VPN, because at least in our research project, we found out that it's not really there in many of the implementations. And the last one, but maybe not the least one, the usability. The home user should not really need to know anything about IPv6 VPNs or other these technologies. He or she should just click it and it should work there. Okay, and then the conclusions. Well, it's a nice proof of concept. It proves that these technologies, components already exist. We can use them to bring enhanced connectivity for home users, and they can be integrated to one this kind of consumer-like device. The important question is, will this solution be adopted? Who will do it? How to make this concept more appealing for adoption? And the most important part of the future work is to find out how to demonstrate and convince vendors and maybe users that this concept and these technologies bring them so many advantages and interesting opportunities that they are willing to have and adopt the solution. So we actually need those applications to run on top of this and IPv6, so that they see that, okay, there we have a cool application, for example, with some community service provider. How could we use use that also in other places. And actually, what I see that how this can be is by continuing this work to integrate and polish the concept, at least on some platforms that are already available, and kind of demonstrate and tell about that this is actually possible. Okay, more detailed information is available in the full paper, and of course from me, and then I will be happy to answer any questions if you have one.
Good morning, Cameron Zekon from the Belgian government. Within your research, what are the actual residential application or residential services or residential devices that you have tested, like for instance, maybe PVRs or TV streaming or IP phones or some other things? So what are the current applications that you may have been using to your testbed?
Well, this research project was this kind of joint research project with Helsinki University of Technology, us and then also a few other places, and also this kind of some of equipment vendors, some of operators, and this Finnish research organization Tekes. And what we did in this project was that we researched mostly about how to make the connectivity there. We tested some of these kind of streaming applications, very simple one like Icecast, Apache servers, WebDAV, the file serving, for example, utilizing WebDAV for this kind of content sharing and these issues. We are now continuing this project in that sense that we are concentrating in this kind of content sharing. And I think we will utilize now this connectivity as an enabler to do this kind of content sharing research.
Because just in order to really deploy and push it, it should not be only application that on our side, administrator, we like to use and we like to play. It should be application for end users so that they will start because they will ask for those applications.
Yeah, that's true.
Hello. The 624 addresses was an option, or did you have an hard time getting 2001 space?
Sorry, could you repeat?
The 624 addresses, 2002,
Yeah.
was an option of the project, or did you try to get 2001 space and was hard to get?
Well, actually, this 624 was chosen that we could then say that this can be done in every operator ISP network, at least in Finland, because you can get the 624 work in every place. But most of these operators, they won't offer this IPv6 to the regular consumers. They might offer it as an experimental service for companies and those willing to ask for it, but most of them don't sell it as a production service.
One last question. What you're explaining there seems very similar to mobile IP. I was just wondering how it differs really. I mean, all I can see is that it does this very similar thing, but doesn't offer the ability to change your address, your location, but keep your address. So I was wondering why you went for that approach rather than mobile IP.
Well, actually, let's see. Right. Okay. To utilize, do you mean mobile IPv4?
Well, yeah. So no, mobile IPv6, and then you would tunnel it. So you tunnel it.
Yeah. So when we are, for example, in this kind of a Wi-Fi hotspot, which there is a NAT there, and we have a private network there, we should somehow get the IPv6 connectivity or the mobile IPv6 connectivity there. There might be an option. It's not a very nice one. It's kind of ugly. But we could do so that we get this IPv6 address from the home network to terminal here, and then we would utilize, for example, home agent in this home router. That this would register the address there, and we would have mobile IPv6 over this IPv6 over VPN solution. But of course, this brings so many layers and so much encapsulation, so I don't know how it would work. But at least one of our ideas was that we could try it to do it.
Yeah, it would probably be good to compare it, maybe see how they differ in terms of performance.
Yeah.
Your technique compared to mobile IP. So.
Yeah.
Okay, thanks again to the speaker. Our next speaker is Ben Mccarthy from Lancaster University. He's a specialist in network mobility and ad hoc networks.
Okay, yep, so I'm Ben McCarthy. I realize that I'm the only person talking about ad hoc networks at this conference, really. It seems to be a very sort of fixed network-orientated conference. I came in Poznan, and there was a few mobility-related sessions, but they seem to have been weaned out now. But so I can make assumptions somewhere, and I'm going to try and not do that. I'm going to try and assume that you aren't all in the mobility area. So the overview of my presentation is I'm going to talk about this mountain rescue scenario that we have. It's basically trying to enable network mobility in a very difficult terrain. So the theory goes, if you can get it working in a mountain rescue scenario, you can get it working in many other areas, such as the military, and then far more simple scenarios like vehicle networks and things. So I'll introduce that. But the basis for the mountain rescue scenario is to provide input into the MANEMO-based research. I'll go into what MANEMO actually means in a minute. And then the interface software that we've provided, which is an example of the sort of applications that we can provide to the mountain rescue team using this networking technique that we're talking about. Then the second part is specifically about MANEMO, about this combination of MANE and NEMO, which is mobile ad hoc networks and network mobility coming together. I'll go more into that further into the presentation. It's a bit early to talk about that right now. And then finally, I realize I've been putting this session, which is IPv6 Dead or Alive. All of my work is in using IPv6, and everything I do day to day is in the IPv6. So I'll give my perspective on these things. So the mountain rescue scenario, providing these guys with a realistic IP communication model on the mountain can offer them so many excellent services. Just alone, the main one, the initial driver is location information for us. If we can provide them with if we can provide them with GPS devices and then have those GPS coordinates sent back to a central location, we can track all of their movements, and which seems simple enough. You think, okay, we'll know where they are. But once things like fog descend, people, you lose the location of people. But not only that, you lose an idea of where people have searched. So people can search over the same areas multiple times. They can completely miss out certain areas. And an ideal directly with these guys, and at the moment we haven't rolled out this, as I'll go on to talk further in a minute, but we haven't got a fully working solution of this model yet. But for now, they send me their GPS coordinates directly, when they have a mission, they send me things offline, so to speak, and I'll sometimes get reports when someone's died or someone's been critically injured, and you start to realise the importance of this, and these guys will then say, had we had some way of knowing, we could have maybe found them in this. We've eventually found them in this location, but it was an area that we'd missed. So the collaboration I have is with the Cockermouth Mountain Rescue Team, which is in the Lake District in the UK. It's nice because the Lake District is a mountainous area, but it's a good place to start because it's not quite like the Alps or such extensive terrain like that. It's a sort of middle ground. So the communication model is basically based on trying to bring the network to the mountain rather than assuming we have connectivity from the beginning. And the point there I'm making is this fits many sort of areas like ad hoc networking, but also hastily formed network, which is the new word that people are using to sort of describe the type of networks they want to provide in situations like New Orleans when there was a big disaster, everything is wiped out, and then suddenly we have emergency services trying to keep in contact, and they have no way of doing that. And then also to also make use of anything else that is available as well. So we try and bring whatever we can, but the minute we lose that, if there is anything else, any other type of connectivity available to us, then we'll try to fall back on that. But we try to reduce the amount of time we do that because it implies service degradation and costs. The team that we work with, specifically the Cockermouth one we talk about, is around about 40 members. They tend to search in between 3 to 6 members, so search party teams moving together. And at the moment they have 3 all-terrain vehicles, and they're trying to get funding for a 4th. And I use network mobility in this situation for a couple of reasons. One is because they're a very good candidate for personal area networks. You hear a lot about personal area networks, and they might come in at the consumer level, but on a level like this, or with firemen or things like that, it's a situation where they might have, you can expect them to be carrying multiple devices. So with the Mountain Rescue Team, we're talking about maybe GPS devices, we're talking about sensors on the bodies to measure their temperatures or their heart rates, and you can connect all of those to a mobile router on the person and then ship the coordinates back. And what IPv6 allows us to do in this situation, just to relate back to the IPv6 part of it, is that we can also contact the devices directly without interaction with the individual. So if they have a video camera or something on them, we can come in and reach it directly ourselves because it has its own address. We don't have to perform any sort of netting or port forwarding. It is its own entity. And the sporadic introduction of COTS, commercial off-the-shelf devices. What we mean there is someone can come along, say their mobile router that we've designed is broken. They can come along just with a normal PDA or anything that will support IPv6, and they can actually become part of someone else's personal area network. So they join the network, but without any understanding of the mobility protocols underneath, and they'll get a degraded service, but they'll get service. So this is just a diagram of what the communication model that we're talking about. So at the bottom there we have the headquarters, which are connected to the vehicles, the all-terrain vehicles. And then the idea is to project the connectivity onto the mountain, a large-scale connectivity. And then in between the search parties, they remain connected using typical ad hoc networking protocols and ad hoc networking MAC, like 802.11. We're actually, at the moment, we're at a point where we had initially hoped that by now WiMAX was going to be more prevalent, really, for the point from the vehicle casting the larger area connectivity hotspot, and it's not the case at the moment. So we're now starting to look into maybe an intermediary situation where we might have large-scale antenna or the sort of pump-up antenna on the vehicles, something like that. We're it's just something to stand in until WiMAX becomes more prevalent. And then the secondary communication, GPRS is, you do find it, you can get connectivity here and there, but it's partial, it's not everywhere. GSM you have, so we have a situation with the software, I'll explain in a minute, where it will degrade all the way back down to shipping the GPS coordinates over SMS if there's nothing else it can do. And then satellite is something we take into account, and we actually, we have some contacts with the satellite guys, but really in the working domain for Martin Rescue, it's overkill really, but we include it because of the military ideas. So the underlying networking model is this combination between mobile ad hoc networking, which is a local way of keeping nodes or entire networks connected to one another, even however much they're moving around, because you change the way that the routing protocol works. You have proactive or reactive techniques where you can either send constantly in a far more regular fashion to normal routing protocols, but also in a more reduced way, so you have subsets that do the sending for everyone, or reactive where you only ask for a route every time that the application needs it. And then network mobility, which is a way of, it's actually, I mentioned there mobile IP, I don't know if people are aware of what mobile IP is, but it's similar to what we've just heard in the last talk. And then NEMO is an extension to that, where rather than considering it was a laptop connecting to the Wi-Fi access point, it's an entire network. So consider a bus. If you have a bus with 20 people all connected to a local router, as the bus moves from one access point to another, it will set up a tunnel with the home agent and forward traffic from there. So what that actually means is that the home agent would be on the home network, and you have a permanent place on the network where you are contactable, and everything will be forwarded to your new location. So you're on one network 1 minute, you register that with your home agent. When you move to the new location, you register your new location with the home agent, but packets are still sent there and then ultimately forwarded onto you. So it means that you constantly remain connected, and people can always reach you. The problem with doing that is if you start to consider complex mobility scenarios, like the Martin Rescue one, when mobile networks connect to other mobile networks, but you still want to remain connected to the outside world, which I show here in this diagram, the way that the protocol is set up with tunneling means that you have to tunnel first through the network you connect to, back to the home agent on their home network, and then back to yours. And so with the example you see there, you can imagine a personal area network, so someone with an iPod and a mobile phone and a GPS device getting onto a train network. This is the sort of routing they're going to get, and that alone is quite inefficient. But when you start talking about 40 people along those lines, you get into inefficiencies that can't be tolerated. So what you can actually do is, or what my research is based on, is combining the properties of the MANE, of mobile ad hoc networking in the local area. So if we go back to that diagram, between the two, NEMO 1 and NEMO 2, you'll actually run a mobile ad hoc networking protocol there, but that also interacts with the home agents, so that it has a permanent connection to the internet and a permanent reachability. So anywhere you are, if the entire mobile ad hoc network moves, it's still reachable. It creates, but the work that I'm doing, it realizes the fact that these two are actually mutually beneficial combinations. So we end up with two situations, Nemo-centric MANEMO and MANE-centric MANEMO. So basically the combination, Nemo-centric MANEMO talks about when the MANE protocols are used to improve the Nemo scenario, but then also you can also bring in the Nemo-based tunneling and the home agent approach to provide global reachability to a more MANE-like situation. So their examples would be the personal area network one I just gave is a Nemo-centric one where, on a train or a plane. Intelligent transport services, vehicle to infrastructure, that stands for, I do some work with people from INRIA and Mccarthy Car Consortium as well, where they're looking into using this sort of approach for your vehicles to talk to each other and then ultimately talk to an infrastructure box on the side of the road to maybe tell them about bad road conditions or about traffic conditions. And some set networks this also works for. And then a MANE-centric one would be the mountain rescue, the one that I'm explaining. Fleets or motorcades where entire movements of ad hoc networks want to remain connected, even if they become separated. We can use this technique so that they don't realize they become separated. So it goes along the idea of this entire conference was the transparency of the network. They all appear to be on exactly the same mobile ad hoc network, but really you're using this tunneling and home agent approach to hide that away from all of the participants. So this is the way that we actually do it. It's a proxying approach. I think it's really a bit going into a bit too much detail maybe for this conference, but we use the home agent based approach, and then we proxy from the closest home agent to the nearest, what we call the MFS, the MANEMO fringe stub, so i.e. the collection of networks. So in that situation, you can imagine the collection there being a bunch of cars or any type of vehicles, and if only one of them has a connection out, all of the other vehicles will use that connection out to proxy through that vehicle's home agent out to the other vehicle's home agent, so they all remain connected. And in that situation, it means, for instance, if you had a car, your family are driving in a car, they're on a road, they don't have internet connectivity, but 3 cars down, someone does. You can hop your connectivity through, but what the traffic will actually do is go via this home agent, so that no matter if you're suddenly not connected to one car, you move to another car, or if you move to an entirely separate connection of your own, all of it is transparent because everything is going via this home agent. So how this applies to the mountain rescue scenario is that we have the same situation, but the home agent is based in the headquarters of the mountain rescue team. And the way we use it is, if you see what is called the MFS there is the on-mountain network. But then if one of those people is searching in an area where they lose connectivity back to the rest of their team, we want them to roam onto a GPRS network or a satellite network or anything they can get, but we don't want the rest of the network nodes or the network entities to realize that fact. We want it to be hidden from them entirely. And the way that we do that is that when it moves off onto this third-party access network, it reconnects to the home agent, and we have 2 tunnels going into the home agent. The home agent advertises reachability to the new location, and as far as the rest of the nodes are concerned, they just see a route. So it means nothing to them. All they want to do is send packets. Well, this is really taking it further with complexity wise. I won't go into too much detail, but it basically when you have multiple rescue teams. So in our situation, we work with Cockermouth, but if search gets very difficult, or it goes on for a long time, or it spans the area that it spans is very large, they'll call up the Keswick Mountain Rescue Team or some other one in the local areas, and they'll work together. So the interface that I was talking about, the application, is the fundamental thing that we're trying to provide is the mapping of where people move, where people are in real time, and where they've been. That is the main goal of the interface, but there's also other things. So when we have mission playback, so that after a mission, the entire team can come back, replay what they've the mission that they've been on, and see what they've done, where they've maybe gone wrong, or where they could improve. We've also got distributed client support at the moment, where we pump out all of the coordinates to a handheld device, so that the on-mountain rescue team can see what's going on, not just the coordinator. At the moment, we only support Windows devices, so we're trying to port that to Linux at the moment. And we keep a database of all of the rescue team, and we have novel things like geofencing. So if one of the mountain rescue team starts to walk near a hazardous location or somewhere that they know that a rock has fallen recently and one might fall again, it pops up a warning to them telling them about whatever has happened. And we also we've done testing with video conferencing between, well, not conferencing, but video streaming between each of the mountain rescue teams, so they can see what the other one is seeing, or voice. These are all future applications that once you have the IP infrastructure in place, it's easy to support. But the main thing is the latencies and bringing those down. So this is just a screenshot from that. You can see we've got traces in color of different. This is actually from one of the offline GPS coordinates tracks that they've sent me with 4 different people on there, and it's one of the playbacks. So we're sort of 11 minutes 38 through a mission, and we have the 3D image on there as well. So finally, I'll wrap up by talking about what my experiences have been. And also my discussions with other people in my department, especially we have a professor at Lancaster University, Steve Pink from America, and he was actually involved in when it was IPNG, in the actual documentation writing. And we had a good debate about this. I told him I was going to be in this session, and we discussed things. So it comes from that discussion, really. So as you heard in the first presentation, the exhaustion of the unallocated pool 2010, according to Jeff Huston, who is by all means probably one of the most up-to-date people in the area. But that doesn't seem to be enough of a driving factor up to now. I mean, that's always been the thing that's been quoted, but we aren't getting take-up because of it. So why not? Well, we've got no demand from the end user is truly one of the main problems, because as we all know, the idea is that we want to just provide them with services and apps, and it doesn't matter how we do that, we just have to. And we have no way of distinguishing between what we can provide in V6 and what we can provide in V4, because at the moment they're very similar. V6 does provide us with tools to do mobility better. So hence why Nemo base spec is in V6, and they retrofit it to V4 because of things like stateless auto address configuration, where we don't have to contact any third party or third entity. We can build our addresses as soon as we move into a new network. So V6 provides us tools like that for mobility. NAT unfortunately, is seen as a useful tool by a lot of sysadmin, security tool, because they don't, sysadmin prefer to think that devices on their network aren't directly contactable, which is completely against what the IETF view of what the internet should be, but this is what such is life, and this is what it's become. I'm just going to skip that and go to one of the important points is that it seems to be there's a conflict of interests. We have vendors on one hand and ISPs on the other. Vendors have spent all this money. I mean, in all of my research, I'm sponsored by Cisco Systems, so I use a lot of their stuff. I've used Linux, Windows, everything that I used, all the IPv6 stuff, all the apps, everything. It all works as well in a testbed situation. It's all very good. So there's a lot of time and effort that has been spent porting things and ensuring that all these things work. And vendors now want a return on that investment. And if this comes off, they can make money from, as I say there, from some like retraining. I mean, so the simple things like the longer address space is actually, it's quite hard to deal with when you're dealing with it every day. If you're talking to someone and you say, oh, can you just ping this address for me, please? Yeah, what is it? 2001, FFFE, it takes forever. So it's not as simple and things like that. Simple barriers along those lines why network admin people don't want to bring these in. And then on top of that, so ISPs are going to bear the brunt of these costs. You've got all this money that the vendors see that they can actually make. It's all going to be coming. The main people it's going to be coming from is the ISPs. And then finally, an important point is that we have a demand and supply situation where ISPs are making money. And this was one of the points of the guy I just told you about. That they're making money from static IP sales because there's a demand, and it's increasing demand, and a reduction in supply. If you bring in V6, you remove that. You flood the market with supply, so the demand is fulfilled, and you reduce their ability to sell these IPs for such prices. So what could change that? So in what I'm showing you here, this mobility examples, mobile phones, for instance, if all mobile phones became fully working internet entities and they had fully working IP stacks on them, and therefore all needed to have an IP address, you get 1 billion, 2 billion mobile phones suddenly, and you get a sudden need of IP addresses, which V4 would struggle with. But then also, more relative to my work, mobile networks, if this work starts to take off in a big way, which, I mean, so the people I've talked to, the car-to-car network are using V6. I mean, the people involved with that are like Audi, Fiat, big names, so they're pushing for this. If that comes off, you not only need a address per vehicle, you need an entire prefix per vehicle, because they want to be able to reach every device on the vehicle network. So you're talking about far more you're using up a lot more of the address space. And then again, same thing, personal mobile routers. I know I've seen presentations from Nokia where they're very interested in serving content from an individual, so serving things from their iPod or along those lines. And finally, there could be unknown technologies. Van Jakkensen's talking about a TCP stack per core. It might be the way to go in terms of efficiency in static networking. So if you're talking, you know, we've got examples of 32-core working architectures now. If you scale that up 2-3 years' time and you've got a TCP stack which requires an address per core, per machine, then you've got massive address saturation. So finally, I'll just tell you about something if you are interested in IPv6. and you want to see how things are going, there's something called the Great IPv6 Experiment, which can be found at www.ipv6experiment.com. And it's a simple concept. The idea is to offer a high-demand service, but you can only reach it over IPv6. It's from the guys at your.org, and what they're going to do is going to monitor the usage, how many people they get connecting, problems people get with tunnels, and what they're going to serve you with is 10 gigs worth of porn. So that's yet to, they're going to do that at some point soon, and hopefully they're going to try and sort of work out exactly where things stand in the internet today with IPv6. It's an interesting experiment. So there we go. I hope I explained it well enough for everyone, and if there's any questions.
No questions. Well,
So in this mountain rescue scenario, in which parts did you use IPv6 and did you have to use IPv4 somewhere, for example, with the cellular operators network?
Yeah, so when you roam off onto the GPRS, we have to tunnel at that point. You know, we hope at some point, so in the primary communication model, we use native v6 all throughout because it's our equipment, so we have that choice. But when we roam onto a cellular network, we have to tunnel over it, and we hope, you know, it will become native in the future. But
Okay, thank you.
more questions? Well, just a small question, or it's more a comment. You said vendors put a lot of effort in applications to make them IPv6 ready. Well, I see this, but my perception is that some of these applications I use still have problems with IPv6, and I think it's due to lack of testing, because these things are mostly tested by the end users, and this is a problem sometimes.
yeah, and they're not getting that much use at the moment. Yeah, I mean, it's simple, isn't it? That if it's not being used as much, then they're not going to spend as much time testing these things. So.
And you know what happens if you have a problem with an application, the IPv6? Your operators just tell you, oh, just switch off IPv6. Nobody uses this anyway.
Yeah.
Okay, that's it. Thank you for attending this session, and thank you to the speakers.
Oh.